So last meeting, we have discussed our first sample problem for reactor design for single reactions. And we started with the CSTR. Okay, this is our sample one. And these are the key points that we have, or these are our takeaway points, the learnings that we have extracted out of the first example. Now we go to our second example. So this time it talks about the this is still about the mixed flow reactor. Okay. Oh, can you see? I put it on slideshow. Can you still see it, class? Are you able to view it? Can you see the slide on example number 2?
Yes, miss.
Okay, so it's better that way because it's bigger. If it will not transition, just let me know. So we have here a pure gas, a pure gaseous reactant A with an initial concentration of 100 millimole per liter, which is being fed at steady state into or steady state rate into a mixed flow reactor of volume, which is 0.1 liter. Now, it dimerizes according to the stoichiometric equation 2 moles of A, forming 1 mole of R. Now, for different gas feed rates, the following data are observed. So, for different V sub O, that is. So, the gas feed rates here that are being referred to are the volumetric flow rates. So, for a volumetric flow rate of 10 liter per hour or 10 liters per hour, this is the final concentration of A in millimole per liter. So 85.7. Now we have another run at a different volumetric flow rate. So at 3, and this is our final concentration for A. Another run, this time a little bit smaller, 1.2 liter per hour is processed. So the final concentration is 50. And we have here the last run, the fourth run, only processes 0.5 liter per hour of feed. And this is the corresponding final concentration or the remaining concentration of A. Now, in this case, you are to determine the rate equation for this reaction. Now, this time, unlike the first example, it's asking for the rate of reaction in terms of A, B, and C. This one, it's specific that it's asking for the rate equation. So the rate equation here is the rate law. You can have it answered in the form of the rate law, or you can have it answered in terms of the differential equation. So let me use the Jamboard for the solution of this. Class, wait, I can't see my Jamboard, so I need to open first Jamboard. Okay. Here we are in Jamboard, and we are to write the information available for us to use. Okay, this is still a problem on mixed flow reactor. So we have the given. We'll write the given information for the said problem. So if I will read the problem, pure gaseous reactant A with an initial concentration of 100 millimole per liter is fed at steady state rate into a mixed flow reactor of volume 0.1 liter, where it dimerizes using the equation 2 moles of A, forming R. So we'll have here our reactor. And the statement starts with pure gaseous A, meaning initially you don't have any species other than A. And this reactor, a CSTR, is processing a gaseous feed. So meaning the reaction facilitated inside the reactor is not liquid in nature but gaseous. So the initial concentration of A is given at 100 millimole per liter. Now, the volume of the reactor is given on the first statement, and it is 0.1 liter. The reaction is given, stoichiometric equation is given, 2A forming 1 mole of R. Okay, so those are the things that we can get from the first statement. Now we have this table. I'd like to write the table here so we can go back to this later. So we have here V sub O in liter per hour, and we have here C sub A in millimole per liter. So these are different runs. So we have here 10, we have here 3, we have here 1.2, and we have here 0.5. And based on these runs, these are the measured remaining concentration of A. So the unreacted A. So these are the information that's made available for us to use. We are after the rate equation. Okay, so we go to our solution. Now you are after the rate equation, and would you know shall I say the order of the reaction in terms of A in this case? Is the order of the reaction in terms of A given in this case? This is your stoichiometric equation. Does the problem give you the order of the reaction in terms of A? Jean Albert. Does it give you if the problem gives you already the order of the reaction in terms of A, then it won't be asking for the rate equation anymore, right? Because the rate equation will simply be expressed in terms of A because A is your reactant. So if you're going to write the rate equation, your main problem is the K, the rate constant, and the order of the reaction. So if I'm going to ask you again, did the problem mention whatsoever the order of the reaction in terms of A? I don't happen to read it. This is the problem. Pure gaseous reactant A is fed at a steady state rate into a mixed flow reactor where it dimerizes. For the different gas feed rates, the following are the data obtained. These are the data obtained. So of course, the problem does not give you the end because it's still something that we need to determine. It's not based on the stoichiometric equation because the problem does not specify that your reaction is elementary. So if it's the rate equation that is being asked or the rate law, there are two things that you need to determine. What are these things that you need to determine? If you are after the rate equation, what are these things that you need to determine? You need to determine the Patrick. What do you think are the two things that we need to determine if the rate law or the rate equation is being asked? Okay, so I have answers here already. So correct. You are going to look for the order of the reaction, that's N, and you are going to look for the rate constant, which is K, for you to be able to determine the rate equation, or you'll be able to write the expression for the rate equation or the rate law. So we're going to do that. Okay, so we go to our solution. Now, how would you start solving this problem if I'm going to ask you in order for you to determine the K and the N? Are you going to start solving the problem? Um, Ezra, how would you start solving the problem? Let's say, typical of a student, at first, you won't know how to solve a problem. So where will you start? What's your starting point? Ezra? Find K. How will you find the K? So what's your starting point? What will I write here first if I need to find the K? What will I write first if I need to find the K? Let's say you do not know what to do. What will be your starting point if you don't know what to do? Because more or less, if you have it written here, uh, probably it will give you some sense of direction. So what will you write first in here? Your first line of solution would be the what? John Vincent. Hmm? You will write the E sub A. The E sub A is the activation energy. You will write the via. What will you write? For you to be able to find your way through the K and the N, what will you write? Via ginto. Johan, what will you write? What's your starting point? Remember, we are already on reactor design. And the information made available for you is volumetric flow rates and concentrations. So you have to write XA, RA, performance equation. Correct. You are to start with the performance equation. Let's see what will the performance equation lead you to, whether it will help you lead to the thing that you are looking for, or you need to work on it parallel with another equation. But you won't know that unless you start somewhere. So you write your performance equation. That's always your compass that tells you, that gives you, probably in my case, that gives me a sense of direction. Because if it will not work for me, then I need to look for another equation that I can work with together with that particular working equation or performance equation. So what we do is we write the performance equation. Our performance equation for the mixed flow reactor is what? What's our performance equation for the mixed flow reactor? Jelaine? What's our performance equation for the mixed flow reactor? Hmm? Jelaine, or can I have Johan again? Bergavera? What's the What's the performance equation? CaOXA. Correct. CaOXA over the rate is tau. Your tau is equal to CaOXA over the rate. This is your starting point. Okay? That's your starting point. Now, this tau is V over V sub O. Now, this CaOXA can be expressed in terms of what? This CaOXA can be expressed in terms of, based on the given. So I'll go back to the given. CaOXA can be expressed in terms of the what? The amount reacted could be expressed in terms of CaO minus Ca. Correct, Jericho. No, correct, Jericho. Drexel. So you express your CaOXA this way. So it's CaO minus Ca. Initial concentration minus final concentration over the rate. Okay? Now, this is what we're going to do. So I'll have now for each of the runs, so I'll place here. So for run 1, 2, 3, and 4, I will have the rates. So these are the rates that I'm going to write in the second row in here. Okay, how will I do that? I'll use this particular equation. So for run 1, the volume of the reactor, so I'll place here 1 so you would know. For run 1, the volume of the reactor is 0.1. It's fixed at that. And your volumetric flow rate is 10. So divide by 10 equal to your initial concentration is 100 millimole. The final concentration, you take it from the given 85.7. 85.7. And you will have here a corresponding rate expression. The rate expression that you will be getting is, can you please give me the rate expression? Now, the quantity, I'm saying expression. It's the quantity because you're going to solve from here. What's the rate? 0.1 divided by 10. That should be used as a divisor to the difference of 100 minus 85.7. What's your answer? Do you have your calculators with you, class, or you don't hear me? Your rate is 1,430, so you write it here 1,430 for run 1. Then the second would be, you will have still 0.1, but this time it would be divided by this, 3. So you have 3, and your initial concentration would still be 1, but your final concentration would be 66.7. So you have, sorry. So this would be 66.7. It will be giving you the second rate. That would be 999. 999. So you write here 999. Check. Okay, the first one is, so I got your answer. So for the third one, you still have 0.1, but this time we divide it by 1.2, and the final concentration is 50. So this is 1.2. I still have your 100 minus 50, and you have your third rate here, value. $600. Okay, for the fourth, okay, so for the fourth, you have same thing, 0.1. We divide it by the 0.5 and 33.3 for the final concentration. So 0.5, 100 minus 33.3 over the rate. Wait, if it's 33.3 or 33.4. It's 33.4. So I have now my rates. My rate here is, so you have here 333. Now, what am I going to do next? I already have the rates, 600 and 333 here. So based on what you have learned in kinetics, few weeks ago. How will you find the necessary K and N in this case? What will you do? You already have the rates, so what will you do? Anybody? I have already the rates. So what will you do? What will I pair these rates with? That way I can find the K and the N. So I have here the rates. I'll pair it with the what? 1, 4, 30, 999. So I have 1, 4, 30, 9999, 600, and 333. What should be the other information here? We're done with kinetics. That way I can determine the K and the N. Think. Use what you have learned last week, other weeks ago. Concentration. Correct. You need the concentration. So meaning the concentrations that we used here, I will pair with the rate. So 85.7, 66.7, 85.7, 66.7, and I have 50, and I have 33.4. Now, what am I going to do with this? Rates and CA. I have read somewhere here. I'm going to what? Remember, my goal is I'll find the N and the K. How will you do that? You're given the rate and you're given the CA. What will you do? You will remember your rate law will be written generally like this because we don't know the K and the N. How am I going to find the K and the N? Plot. What will I plot? We will not plot. I told you we will not plot. What will we do? Will not plot because if it's going to be plotting, it will take some time. You use your calculators, you use linear regression. What will I do? ln, correct. I will take ln of both sides. So I'll take ln of the rate. That would be the ln of the K plus the n ln of CA. This is now comparable to an equation of a line which I have shown to you when we were discussing kinetics. This is the y of the line. This is the x of the line. This is the slope of the line. And this is the y-intercept. So meaning, you are going to go back to this pair of values that you have and get the ln of RA and get the ln of CA. So we're going to do that. So if you're going to get the ln of RA and the ln of CA, we'll have another table here having 2 rows, but this time you will have the ln of the rate and the ln of the CA. So we'll get the ln of 1,430 and 85.7. Can you do that, Aina? ln of 1,430 and ln of 85.7. Next would be the ln of 9999 and ln of 66.7. That would be Drexel. The ln of 600 and the ln of 50. That would be Vincent. And the ln of 333 and together with the ln of 33.4. Place it there in the chat box. That would be, whose name have I called? Jericho. Have I called Jericho? Can you get the LNs and then place it on the chat box so I can place it in the new table here? So for the first pair, it would be, I forgot whose name did I say. Then
Hi,
second,
Miss.
Okay. Can you place it on the chat box, please? ln of RA and ln of CA.
Miss, pila ka decimal places?
2 will do. Okay, wait. Drexel is 6.9 T 9068. And 4.2002. 7.2654 and 4.45. Next, Vincent, you have 6.39 and 3.91. Okay. You have 5.80, 81, and you have 3.5086. Thank you. So we have this now. What do we do with this? This is your y. This is your y. And this is your x. What will you do? You use the linear regression in your calculator. You find the slope of the line. That would be the order of the reaction already. Then you find the y-intercept of that same line. That should give you the ln of k. If you raise that to, or if you make it as the exponent of the e, the value of the ln of k, that would give you the k itself. Okay? Now, can you do that? Can you find, okay, I'll call another name. Find the n using the slope of the line that you have. That would be Ezra. And for the K, that would be Johan. Can you place it on the chat box? The others can check it as well from your end. If you do linear regression, what would be the slope and the y-intercept of your line? Do you have it already? Would you know how to go about it? Can you please let me know in the chat box so that we will not waste time on this if you still do not know how to go about finding the, using linear regression in your calculator and finding the slope and the y-intercept. Okay. I have an answer here already. Can we check? Thank you, Ezra. So the y-intercept is, so that would be the ln of k is equal to 0.05395. So if that would be, if we're going to get the k only, this value should be the exponent of the e. So kindly check the value that is provided. So 1.0554. I can't place the unit here because I don't know yet the order of the reaction. What about the others? Is this the y-intercept that you got also? Okay, you need the table. These are already the values because these are already processed using ln. You have the answers already? If not, I leave that to you because I already assigned it to you to check on how you're going to use your calculators using linear regression. Okay, it's not anymore a part of kinetics on how to use your calculators for this particular procedure. You are to do that because you will not resort to graphical in this case because that would take time. Okay, unless otherwise, you have your Excel there in your laptop wherein you can get the equation of the best fit line. Okay, so there were changes in the y-intercept this time. It's 0.02 or point 2. 0.2972. So you'll have here 1.3461. For the n, which is the slope already, that would be 1.5671. So this then must be raised to 1.5671, and this is 1.3461. Now, what should be the corresponding set of units for your K? Then, if the order of the reaction is 1.5671, so what would be the units, set of units for your K based on our formula? Liter per mole raised to liter per millimole. Thank you for that. Liter per millimole raised to, what's the exponent of the liter per millimole? The order of the reaction is 1.5671. So what should be the set of units? Correct, Jericho. That would be 0.5671. And you will have here per hour for the time. Now, this is the common mistake of students. They don't know how to express the correct set of units for the K. I already gave you the formula for this one. So it should be 0.5671 liter per millimole raised to 0.5671 for the units of your rate constant. Okay, the concentration unit is mole per liter, but it's raised to 1.5671. So if you're going to multiply the liter per millimole to that set of units, it will give you a final set of units of millimole per liter per hour. Okay, so this is your rate law. So if it's the rate equation that is being asked, if you want to be very specific on that, this is your rate equation. Negative dCA dt is equal to 1.3461 liter per millimole raised to 0.5671 per hour Ca raised to 1.5671. Okay, so this is your rate equation. If it's the rate law, actually, the rate law is acceptable already. But if it's really equation that we are trying, that the problem is asking, that it should be in the form of a differential equation. Okay? So any question in what we did? Here, for example, problem number 2. Understand? So we go back to our slides. So that's our problem, and these are the key points, the learnings, the takeaway that we get from this particular problem. So we are on sample problem number 2. So it demonstrates that we will need multiple runs. So that is why you're given multiple runs in a mixed flow reactor to arrive at a reaction rate expression. So if the problem is asking for the rate equation or the rate expression or the rate law, the problem should provide you a series of runs or a set of empirical data where you can get the changes in the concentration either with respect to the rates itself or either with respect to the feed rates that were used. In the case of this problem, the feed rates were varied and the corresponding changes in the final concentration of A were noted. That way, we can get the values of the rates, the actual value that is, and from that actual value, working on it together with the concentration, you'll be able to find the order of the reaction and the rate constant. Now, in here, ignoring density changes in the analysis would result to a wrong kinetic expression. Now, what do you think is the essence of this one? What have we done, by the way? In this particular example, I intentionally uh, uh, do it that way. That way, you will know what's wrong with what we did. What is this? Can somebody explain? Ignoring density changes in the analysis would result to a wrong kinetic expression. What is the wrong thing then? What was the wrong thing then? Or what was missed in the computation? The process of determining, I'd like to go back to Jamborna. The process of determining the rate, there's no error in the principle that is being applied in determining the rates and in pairing it with the concentration. That way we can find the N and the K. However, so there's a however, I'll go back to the slide. This is the second takeaway and it's very important. What was ignored? It says here, ignoring density changes in the analysis would result to a wrong kinetic expression. What was ignored? Anybody? What was ignored? Epsilon A. Very good. Why is there importance in not ignoring epsilon A in the first place? I'll go to our problem so you would see. In the original solution that we did, I intentionally do it that way. Now, I'd like to ask you a question. Why should we not ignore epsilon A in this case? So that's your problem. Why do you think we should not ignore it? If anybody, you can write your answer in the chat box. Epsilon A should not be ignored. In the solution, in the process that was illustrated to you, it was ignored. Why should we not ignore it? This is the problem that is given to you. Why do you think is the reason behind it? It should not be ignored. Malain ang rate equation. Precisely, Drexel, malain ang iya rate equation. Ang rate equation nga nakuha naton, hindi na siya amo. So, ginubra ta gidna, ginubra ho gidna. Kay gusto ko mabalaan kung nga kung makainsindi ka mo nga kinahanglan nga hindi siya pagkalimtan si epsilon AXA. So, that is why I'm sharing to you again the problem. Why should epsilon A not be ignored? Or density changes should not be, shall I say, forgotten. It has to be considered. That's the problem that is given to you. Why do you think that in the first place, we should have determined the epsilon A? We were discussing epsilon A few days ago. Why do you think that epsilon A in this case should be considered? Third year? Why kay kamo kay balo nga ang kinahanglan isulbo ng epsilon A dire? Doging emphasize ko man to pag-discuss ta. When do you consider epsilon A and it should not be forgotten? When? Jericho, why do you think that epsilon A should not be forgotten if this is the problem here? Why should we consider it? And why should it be determined first? It should not be overlooked. Because the entire process that we did is wrong. I intentionally do that. Why? Anybody who can answer my question? Because of the pure gaseous na word, miss. No, it's not because of the pure gaseous na word. It's because of the what? It's because of the pure thing you need in determining the epsilon A. The pure, the adjective pure here in the gaseous reactant. But the thing that tells you that you should really consider determining epsilon A is because of this. Your reaction is gaseous in nature. Your reactant is gaseous. Your feed rates are gaseous in nature, or by nature they are gas. So I have emphasized this when we were discussing on variable volume batch reactor data, that whenever the reaction is gaseous, even if the problem is silent about it being constant pressure or variable volume, it is automatic that you determine epsilon A. It is automatic that you should not forget to determine epsilon A. Because if you forget epsilon A, no matter how correct is the process that you did, in our case, kay na wala dito sang wrong. Ang wrong lang kay wala ni siya ma-consider. Wala siya gin-determine anay. If you have determined epsilon A, then you would have worked on a different performance equation. A performance equation that will consider that your reaction is variable volume, meaning your performance equation is not a simple case of rate equal to CaOXA, or rather tau equal to CaOXA over the rate. It would be different. In this case, if you're going to determine the epsilon A, the fractional change in the volume from 0% conversion to 100% conversion, what should be the value of the epsilon A? If I'm going to ask you, what's the value of the epsilon A if you have determined it initially in the first place? What should it be? Negative 1/2. Correct. You will have 1 minus 2 over 2. But that would be negative 1/2. So the working equation, I like to clear the markings here. The working equation for this particular varying volume system that we have will be different. This particular working equation is only for constant volume systems. Constant volume system. So then, where will the error be? Diin ta nagsala, diin ang islanta. Which part of the formula will you change? That way you will be able to account. You'll be able to account for the epsilon A. Where is that part of the formula? You can place it on the chat box. What part of the formula will you change? So you have tau equal to CaOXA over the rate. So which particular part of the formula will you change? What is it in varying volume system formula that we use? So we have two. One is for the volume and the conversion, the linear relationship between the two, and the other one is for the final concentration, right? Tuha lang man na siya ka-formula ang nag-change. Nga i-add-on mo na sa mga standard formula for constant density system. So then, in this performance equation that we have, what particular part of this performance equation will you change? Will it be the tau side? Will it be the numerator side? Will it be the rate side? What will you change? The tau, the rate, which is in the denominator, or the numerator? What will you change? You have CA equal to, oh, thank you, may nag-answer na. Numerator, yes. Correct, Fritz, ang numerator ang islam. So I'm going to write the formula here. If it's constant density system, you have this, right? If it's variable system, volume system, you have 1 plus epsilon A XA. Now, if you'll expand the numerator, you will have CaO minus CaOXA, and you have this entire 1 plus epsilon A XA. Now, what will you do? You transfer the 1 plus epsilon A XA in here. So you have CA times 1 plus epsilon A XA equal to CAO minus CAO XA. If you want this expression, you can have CAO XA. I'll transfer it here. Then you will have CAO minus CA times 1 plus epsilon A XA. This thing that you have in here should be changed to this one, right? But we still have a problem if you change it to this one. What's the problem? If you change your numerator, the CAOXA, to this expression, what is the problem? What is the problem? Correct. The XA is missing. You have nothing to substitute to XA when you will simply substitute this entire expression to this CAOXA. So what you're going to do, instead of replacing the entire CAOXA by this collective expression, which you have nothing to substitute XA for, what you're going to do, it is the XA that you're going to change in here. Anyways, the initial concentration is already fixed. So you're going to determine the XA for each of the runs. Okay? Now, we will do that after the week of the exam. We will redo this wherein we need to first determine the XA for each of the runs. Then see how will our N and K be compared to without considering the density changes. Okay? Since it's already 1:30. So that is how important it is that if you read a problem in kinetics, you have to be very careful, observant of the words that are placed in the problem. So if the problem says gaseous, even if it does not say constant pressure or varying volume, you should never ever forget to account first the epsilon A. Kay kung nasulat mo na naadaan si epsilon A, kabalo ka na nga ang dason mo mga formulas will have to consider it. It should not be forgotten. But if you have already forgotten epsilon A, everything that you're going to do, no matter how right it is, will be wrong because you failed to consider it. Okay, so that's it. This topic on, I will stop sharing.